So in our previous class, we were able to look at the measures of central and the measures of dispersion. And we said in the measures of central tendency, our concern was on the mean, mode, and median of both grouped and the ungrouped data. Then we went to the measures of dispersion. And in the measures of dispersion, we were able to look at the range, the interquartile, the quartile deviation. We were able to look at the coefficient of quartile deviation. And we were also able to look at the percentiles, the quartiles and the percentiles. So today I want us to look at the variation. And I said measures of dispersion basically tends to explain how far are we moving away from the data. For anomaly distributed data, that data is supposed to give you a mean, mode, and median at one point. Normally, we say that data is bell-shaped. So the convergence or the tendency of having the mean, mode, and median at the center is very high. Assuming a class of 100 students, we normally expect that in a performance in a class, we are going to have like 25% of the students will be at the extreme, so they'll score an A. Then I'm going to have like 25% of the students will not be able to score the pass mark. So I'm shading away 25 who will be in the top cream and 25 below. So I expect that my 50 students will be lying in the middle. So even if I was to get the mode, mean, and median, they'll be lying at the same point. That's what we call the normal distribution. So anomaly distributed data, all the metrics that we are going to look for, be it mode, be it mean, be it median, be it what we call the Catalysis, be it the Pearson coefficients of skewness, all of them are supposed to be at the same point. That is for anomaly distributed data. Later on, I'll be showing the images of, because the steepness, again, the steepness of the curve has some meaning. It describes the symmetry. Could be so sharp, or what we call the leptonic. Could be it's so moderate, almost a plateau, or what we call the plateautic. So the normally distributed data will have all the metrics lying at the center or at the same point. Now, I said that we can either go for the entire population, what we call census, or you can do sampling. So even when we are looking at the standard deviation or the variance, we'll be denoting the parameters for population as this. This is what we use to denote the parameter for variation. But when we come now to the sample, we'll be using the S, capital S. So when you are doing statistics, we'll be using S. If it is the census, we'll be using that sign there. I want to call that sign sigma, but it is a Hebrew letter. So let us just use it the way it is. It's a parameter. To mean, for ungrouped data, we normally get the summation of the, this is our, now let me give an example. If for instance, I have these, let me give an example. I have these values that have been observed from a population. So I'm having 30, 32, 40, 48, and 50. They are 5. So because this is coming from the population, the mean for the population, we normally use this sign here. We call it mu. When you come to the sample, we don't use mu, we use X. So when you are talking of the X bar, we'll be talking of the mean of the sample. I remember explaining that in our previous class. So if I was to get the mean of this population, my mean will be, I add all of them, I'm going to get 200. 200 divided by 5 will give me 40. So my mean for that data is 40. If I was to get now the variance, and we said variance is given by the standard deviation squared, we are going to get our mu, which will be subtracted from the, let me indicate the data. Now we've gotten the 40, which is our assumed mean. So I'll be looking at how far I'm deviating. So you said variance is all about how far are we deviating from the mean of the data or from the average of the data. So my average is 40. So my first observation will be 40, will be 30 minus 40, which will give me 10. So I'm deviating 10 steps from the population mean. The second one, I'm deviating 8 steps from the population mean. Because the third one, I'm timing at the same point. The fourth one is larger. So it's 48 minus my mean, which is 40. I'm getting 8. Then the fifth one is 50 minus. So if I was to get the squares, because you said that our variance will be the standard deviation squared, I'm looking at how far I'm deviating, then I square my standard deviation. If I square, I'm getting a sum total of 328. So the summation of my standard deviation squared is 328. The reason why we do the squares is to get the absolute figures. Because in this situation, then the negatives are going to cancel the positives and you are going to have a 0. It will be meaningless in statistics. That's why we normally square the deviations so that we get a discrete data. Are we there? So I have 328. So my 328 will now be divided by what I got. So my number of the data or what we have in our data. So to get our variance, it is 328 divided by 1, 2, 3, 4, 5. Reason being is a population. So we are dividing by the number. Capital N denotes the number of items or elements in the population or the number of observation. So my variance will be 328 divided by 5. What are you getting? Should be 65 point something. So we are going to get 65.6. I want to believe you are near your calculator. So that is the variance for the population. Now the difference between the variance for the population, that's why I came to this example, and the variance of the sample. This is the difference. Now for the variance of the sample, now our mean, we normally get the mean in the same way, but for the sample now you can see it is a small n because we are getting the number of observations out of the sample that we selected. Are we there? So assuming that our sample was n, it will be the sum of all the possible observations. We divide by the number of elements that were being used in the sample. So it follows our variance, which is now standard square, the standard deviation squared, will be now for the sample. It will be We've gotten 328, isn't it? We've gotten 328 as the deviation. Yeah, we've gotten 328 as our deviation, or the standard deviation squared. I want to show you the difference between the population and the sample. For the sample, we deduct 1 from the numerator. So you can see this one, you are working with the entire population. For the sample, we deduct 1. So whereas this was 328 divided by 5, which was giving us 65.6, this one will be 328 divided by n minus 1. So our n is 5. We subtract 1, it will be 4. So you can see the difference. 328 divided by 4 will give us, it is giving me 82. It is giving me 82. So there is a difference between the observations that you are going to get if you are working with the population and if you are working with the sample. Are we there? That is for the ungrouped data. So if we go to the grouped data, the only thing that you are going to introduce to our formula. Now people are wondering why I'm not talking about this one. I've said that variance is how far you are deviating from your mean. And the reason why we have squared our deviation is to avoid getting an absolute 0. So when we are talking of the data having a larger variance, we'll be expecting that for a normally distributed data, or what we are calling a homogeneous data, our data will be what we call unimodal. Unimodal is to mean mean, mode, and median, which are the measures of central tendency, will be at the same point. So for the grouped data, the modal class, the median class, and the mean class will be same class. It's only that we are going to have some variance in the metrics. So later on, I'll be explaining how we are able to look at the data, whether it is positively skewed or it is negatively skewed. I'll be explaining that in the course of this lesson. So we go on. I was saying now this is for the ungrouped data, the example that I've given. Since you said that our population variance is denoted by the standard deviation squared, to get the standard deviation, then I'll need to get the square root of the variance. And this is what you've done here. So for us to get the standard deviation, I'm going to get the square root of the variance because my variance was standard squared, the standard deviation squared. Are we together? So the formula now becomes under the root. So if you look at the formula here for the variance, the formula doesn't have a square root. So to get the standard deviation, I have to get the square root of the variance. In other words, we say that the standard deviation is the square root of variance. So variance is the standard deviation squared. And the reason why we are doing that is to avoid the absolute 0, because it will make our data to be meaningless. I think that is clear. So for the grouped data, I'll just introduce the frequency. So whatever I had, I just introduce frequency. For example, in the sample, for the group data, I want us to concentrate more on the sample because we'll not be dealing with the entire population. But for the entire population, if you were to look at the metrics or if you were to look at the variance of the grouped data for the entire population, it will be now the summation of, now I'm introducing the frequency, because the frequency is what now will determine the class or the class width. So I'm introducing the frequency to the formula. So I'll be multiplying my numerator with the frequency of the particular class. And then from there, I'll be getting the summation of the frequency. I multiply now by the deviation. And this deviation, remember, we are squaring it to avoid absolute. So you can see what is happening to my denominator. For the sample size, we say that we'll be talking of the n minus 1. So n is the sample size, then I subtract 1. So for the entire frequency, for instance, if I had a data that had 100, let me see whether I have an example. But I'll be giving an example later on. So let me not digress. So I've introduced the frequency. So it will be my total cumulative frequency, which is the summation Fi. For instance, if my cumulative frequency is 100, I remember the example that we had in our previous class. If I was to go back, it was totaling to 74. Confirm, it was 74. So it will be 74 minus 1, which will be giving us 73, right? So you can see what is happening to the population. The population is remaining as it were because we are dealing with the entire data. So the same case will happen to the standard deviation. So when I'll be coming to the standard deviation, I'm going to get its square root. Then there is something that we call the coefficient of variation. And coefficient of variation just compares the variability of data, and it is not a unit measure per se. So we'll be looking at the how far percentage-wise is the data moving from the unimodal class. So we normally talk of the coefficient of variation, and it is dimensionless. So we can only talk about the either a percentage or how far it is moving. And this will be covered when we'll be talking about the hypothesis testing. We normally use two distinct measures. We either talk of the 99% degrees of confidence. So we are giving ourselves an error term of only 1%, or we talk of 95% degrees of confidence. So we are giving ourselves a 5% error. For a very well-defined data, we normally give ourselves an error term of plus or minus 1. So we are talking of 99% degrees of confidence. But for a data that is not well sifted, we normally talk of 95% degrees of confidence. And the rationale is a sample size is supposed to be 5% of the entire population. That's why we are talking of the 95% degrees of confidence. So in short and narrow, the higher the coefficient of variation, the higher the variability. If, for instance, I vary data and I get 95%, and I vary another data and I get 93%, it means that the data with higher variability is the most variable data. I have an example here. I've been given two sets of data. One data has a mean of 150 kgs. It has a standard deviation of 30.5. And I have coefficient of variation of 0.23. So you can see to get the coefficient of variation is just the standard deviation I divide by the mean of that data. So B has a standard deviation of 0.015 centimeter, and I have a mean of 0.85. So the coefficient of variance of this data will be 0.018. So if I was to compare, set A has a greater variability than set B. And I have said the coefficient of variation is dimensionless, and it doesn't measure any units per se. It's supposed to be what we call in calculus, what we call hyperbolic. When we are talking of things like cosec and cotangent, we are not talking of the angle theta. Rather, we are talking of not the circle, but we are talking of the curve. So it's like a higher, it's like another perspective of looking at the variation of data, but it's not common. The most common one is variance and standard deviation. So at this point, what I want you to understand is that variance is standard deviation squared. So to get the standard deviation, after we get the variance, we just get the square root of the variance. Whatever we get is the standard deviation. Now, I had talked about the bell shape or the normality of data. And I've said for a unimodal data, the reason why I'm not going deep in this will be covered in business statistics too. So what I'm supposed to do here is to just introduce. We are going to measure the skewness in business statistics too, for those people who will take business statistics too. So we normally say a normally distributed data is supposed to form a bell shape. A bell shape is this shape. So you can see it looks like a bell. You just need to have a handle here. You know those bells that used to be used by the bell ringers in your high school. So we are talking of a bell shaped to mean if the data is unimodal, and by unimodal I mean the mean, mode, and median are lying at the same place. That's what we mean by unimodal. It is going to give us such a shape which is symmetrical. To mean my mean, mode, and median will be lying at the center. And I said for a good class, if you are 100 in a class, we expect at minimum 25 A's. We expect at minimum 25 students will get a supplementary, and at most 50 of the students will pass. You get, that is a normally distributed data. 25% on the extreme, in the middle, we have the 50%. So for a unimodal data, we expect that the mean, mode, and median will be lying here. Time statistics are false. For instance, if students have failed in KCSE, for example, during the Corona year, 2020, you know, Magoha cannot declare that student failed. No, they just look for a standard. They multiply all the results with a standard to ensure that they acquire what we call the unimodal or the symmetrical data. Are we there? So when we are looking at the skewness, we say skewness describes the degree of symmetry in a given data. And this symmetry, or when we are looking at the skewness, now there are metrics that we use, like the Pearson, the first Pearson coefficient of skewness and the like. But you can even use your human eyes. For example, look at this curve. I have number A. You can see it's so sharp, isn't it? That sharpness has a meaning in statistics. Look at B. It's a bit gentle, right? So these are normal distribution, or what we call the mesocaltic. Then we have C, that is nearly flat. You can see it's like it's forming a plateau at the center here. We say this kind of a curve is plateautic. So the degree of the skewedness or the sharpness is what we are calling, or that skewness is what is now describing the degree of the symmetry in the given data. And we said for the unimodal data, we expect that we are going to have the three, that is mean, mode, and median, lying at the center. So that is what we call the skewness. So we are talking of a normal distributed data. And then in this normally distributed data, we want to know, is our mean, mode, and median lying at the center. From there, we now talk of the kurtosis. I want to introduce these jargons, and I want to go slow. Kurtosis describes now the degree of peakiness or the steepness. So we have what you said is highly peaked, this one. We call it leptokurtic, from the word kurtosis. And I've said kurtosis describes the degree of peakedness or the degree of steepness. So it could be highly peaked, could be normal, or it could be slowly peaked. So I've said the highly peaked is called leptokurtic, the normal is mesokurtic, and the one that is yearly forming a table is called platykurtic or the plateau. So when we are talking of the kurtosis, of course, we measure this using what we call the Pearson's coefficient of, so they are here. I had the first graph, the second graph, and the third graph. Now, we normally talk of that data being skewed either to the right or to the left. If the data is skewed to the right, we say that data is negatively skewed. And when we are talking of the skewness, we mean that data is being pulled. The data is being pulled towards the mean, or the average of that data is being pulled toward the skew. That's why we are talking of the degree of skewness. So I want you to watch this. In a positively skewed distribution, the mean is greater than the median, and the mean is also greater than the mode. And our median is greater than the mode. That is a positively skewed. So in other words, our data is skewed to the left because it's like it's being pulled by the mean. So if I was to illustrate, my curve will be looking like this. It will be looking like this. It is negatively skewed. Now, if my mean is less than the median and is less than the mode, now we are moving in the opposite direction. My data will be looking like this. It will move, then skew toward this side. I'm trying to look at the, let's see whether I can be able to illustrate this. Well, let me go back to where I was. So if I was to give an example with this data, we are saying for the positively skewed data, we expect that our skewness, or the degree of skewness, our mean will be greater than the median and the mode. In other words, it's like we are moving our mean on this direction. It will be positively skewed, right? If the skewness is negative, our mode is greater. So it means that the mean is lesser than the median and the mode. So my mean will be pulled on this side. It is negatively skewed. It's not easy to explain the negatively and the, so we have a formula. And this is where we use now the, what we call the skewness, the Pearson. We have the first and the second formula. So this is the thumb rule. Now, if we can either use the Pearson, the what we call the first Pearson coefficient of skewness, or the second one. And we normally use the first coefficient. You can see what is happening. My x, this x is the mean. My xm is the mode. Then I have S is the standard deviation. So in other words, for us to get the first and the second Pearson coefficient of skewness gives us a 0, it means that that data is unimodal. Unimodal means it is lying at the center, so the mean, mode, and median are at the same point. So what we'll be looking for is how sharp it is. So the highly sharp, we said, is the leptocartic. I think I have let me show you. So the highly sharp is what we call the leptocartic. If it is normal, it is mesocartic. You can see for the normally distributed data. And if it is plateaued, we talk of the platycartic. But for you to get this, that's what I'm drawing at. If your data is lying at the center, then your first Pearson coefficient of skewness will give you an answer 0. If it gives you an answer that is greater than 0, the distribution is positively skewed. If it gives you an answer that is negative, then your distribution is negatively skewed. So we adopt the formula. Now, the first formula, you can see we are talking of the mean. We subtract our mode, divide by the standard deviation. The second coefficient of skewness, we use 3. Then we have the mean minus the model class, divide by the skewness. Again, we reserve that for business statistics too. What I needed you to appreciate is the bell shape and how, and this will be a question I'll ask in the exam. So I'll ask you to illustrate the 3 outcomes of anomaly distributed data. So I want people to draw these 3 images. So the first one is the leptocartic, then we have mesocartic, and we have the platycartic. Any question? Any question? No question. Our next topic is probability, and that's what I want to introduce. Our next topic is probability. You go to the portal. I had given the objectives that we need to, but the probability that we'll be talking about here will not be interested in the, I know you people did the tree diagrams and whatnot in your Form 4. We'll be talking about the probability distribution. And we normally say probability is the measure of likeliness that an event will occur. I'm trying to fetch my notes. Let's stop to share. For my notes for probability. Yeah, here I am. To confirm, you can see my screen. So I've said that probability is the measure of the likeliness that an event will occur. For example, if you toss a coin, you know a coin. If you toss a coin just once, it's either you are going to get the head or you are going to get the tail. The head is where we have the president or the image of the president for Kenyan coins. On the other side, we have the image now, or we have the emblem of the country. In the new coins, we don't have the president. I think we have the figure, but that's basically what we mean when we are talking of the head of the coin. So I'm going to have chances of half-half. I can either get the head or the tail if I do it once. Now, when we talk of the probability distribution, I'm trying to look at some terms that I needed to explain before we come into the distribution. There are some terms that we'll be using in this class that are very...
Excuse me, teacher.
Mhm.
I can't see your screen.
Yeah, I've removed it because I want to share something else. You can now see it, right?
Yes.
Those people who are wasting time, writing me charts. I said we got to be behaved in this class. I don't read those charts. Just put your mic on, ask what you're asking for. You can see how I'm trying to move from one screen to another. I wouldn't have any time to look at the chart. Kindly. I think it's something that I repeated in the morning, but people never learn. Anyhow, I've said we are supposed to cover probability distribution, but because I want to bring you closer home, I've said probability is the measure of the... Now I normally compare. Now you can imagine if the teacher, let's say, enters the class, assume you are in a face-to-face class. Mr. Mbogwa enters there wearing earphones. When you ask a question, instead of answering you, let's say we have a WhatsApp group. I go to the WhatsApp group and I start typing. It is so unethical, to say the least. I've given you the right to ask that your mic is open. I've not restricted anyone in this class. I've even given Zaitun the right to underline my notes. You can see how she's underlining my... Zaitun, how do we help you? Zaitun. We'll assume it is by mistake. Huh? So probability is the measure of the likeliness that an event will occur. For instance, the probability of raining today, is half-half. It can rain, it might not rain. So the probability is 50-50. So a probability is a way of assigning every event a value between 0 and 1. And I know you know this. When we are talking of the probability, we'll be talking of between 0 to 1. So if the probability of an event occurring is 70%, chances that it will not occur will be 30%. It cannot go above that. So we talk of the values between 0 and 1. So to qualify as a probability, we assign these values such that these events are mutually exclusive. In other words, we are taking events that don't have a common result. And the undertaking of one event doesn't depend on the other event happening or not happening. And that's what I want, or those are the terms that I want to introduce, because they are terms that we'll be using in this class. They are English terms, but they have a meaning mathematically. For example, when we are talking of the independent events, if two events, A and B, are independent, then the joint probability of those events will be half-half. In other words, we use this sign to depict and. So when we'll be talking of events that are independent, we normally use this sign, right? And we normally get the product of the two events. I've given an example. If two coins are flipped, the chance of both becoming head is half-half. We say the chance of getting a head is a half. So you can get two heads, you can get two tails, or you can get one head and one tail, isn't it? Those are independent events. Then we have mutually exclusive events. If either event A or event B occurs on a single performance of an experiment, we say that these events are union of each other, and we denote them by this sign. This is union.